When upgrading the electrical system in an older home, ensuring proper grounding is crucial for safety. There are shortcuts to avoid and methods to consider, all while adhering to electrical code requirements. Firstly, it's important to address the dangerous shortcuts that should never be taken. Replacing 2-prong ungrounded outlets with 3-prong outlets without actually connecting a ground wire is a common mistake. This creates a false sense of security and doesn't provide any actual grounding protection. It's dangerous and ineffective and should be avoided at all costs. Secondly, using water pipes as a grounding conductor is prohibited by electrical codes in most jurisdictions. Water pipes can corrode or be replaced with non-conductive materials like PVC, which would interrupt the grounding path. This presents a significant safety hazard. Thirdly, grounding to gas pipes is extremely dangerous and strictly prohibited. Gas pipes carry flammable materials, and using them for grounding can create a fire or explosion hazard. Lastly, using oversized ground rods in an attempt to improve grounding can be counterproductive. While it may seem like a larger rod would provide better grounding, it can actually increase resistance and reduce the overall effectiveness of the grounding system. Now, let's discuss some acceptable methods to consider when retrofitting grounding in an older home. One approach is to install a retrofit grounding system. This involves running a separate grounding wire from the electrical panel to newly installed ground rods. A proprietary system known as ESGround is one example of this type of solution. This ensures a dedicated grounding path, improving safety. Another approach is to install isolated ground rods near the electrical panel and connect them to the existing grounding electrode system. These rods supplement the existing grounding, providing additional protection. This can be particularly useful if the existing grounding is inadequate. Hammer-driven ground rods offer a convenient alternative to traditional ground rods, especially in tight spaces. These rods are designed to be easily driven into the ground using a hammer, simplifying the installation process. Several important notes should always be kept in mind. Firstly, it's crucial that all grounding work be performed by a licensed electrician. Electrical work, especially grounding, requires expertise and knowledge of local codes. A qualified electrician can ensure the work is done safely and correctly. Secondly, grounding is essential for electrical safety and should never be compromised. A properly grounded electrical system protects against electrical shock, reduces the risk of fire, and helps to ensure the safe operation of electrical equipment. Thirdly, ground fault circuit interrupters, GFCIs, provide personal protection by detecting ground faults and quickly interrupting the circuit. However, GFCIs do not replace proper grounding. GFCIs protect against electrical shock, but proper grounding is necessary to clear faults and prevent property damage from fire. Lastly, regular inspection and testing of the grounding system is crucial to ensure its continued effectiveness. Over time, connections can corrode and ground rods can deteriorate. Regular inspection and testing can identify potential problems and ensure that the grounding system is functioning properly. By avoiding dangerous shortcuts and implementing code-compliant grounding methods, the electrical system of an older home can be significantly improved, enhancing safety and preventing potential hazards. It's imperative to hire a licensed electrician, follow all applicable codes, and prioritize electrical safety. A properly grounded electrical system is a critical investment in the safety and well-being of the occupants and the protection of the property. Therefore, never compromise on grounding, and always seek professional guidance to ensure a safe and compliant electrical installation. Grounding works by providing a low-resistance path for electrical fault currents to flow back to the source. This low-resistance path allows the overcurrent protection device, such as a circuit breaker or fuse, to quickly trip and interrupt the flow of electricity during a fault. Without proper grounding, fault currents may take unintended paths, such as through a person's body, resulting in electrical shock, or through building materials, leading to fire. The grounding electrode system typically consists of one or more ground rods driven into the earth, a metal water pipe that is in direct contact with the earth for at least 10 feet, or a concrete encased electrode, often referred to as a UFA ground. These electrodes are connected together into the electrical panel using a grounding electrode conductor. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. In addition to the grounding electrode system, the electrical system also includes equipment grounding conductors. These conductors are typically bare or green insulated wires that run along with the circuit conductors to electrical outlets, appliances, and equipment. The equipment grounding conductors provide a low resistance path for fault currents to flow back to the electrical panel, allowing the overcurrent protection device to trip. When retrofitting grounding in an older home, it may be necessary to install new equipment grounding conductors. This can be done by running new wires from the electrical panel to the outlets and fixtures, or by using a method called ground wire augmentation. Ground wire augmentation involves connecting a new grounding wire to an existing metal junction box or conduit system and then running that wire to the grounding electrode system. This method can be used to improve the grounding of existing circuits without having to replace all of the wiring. In some cases, it may not be feasible to install a complete grounding system in an older home. In these situations, ground fault circuit interrupters (GFCIs) can provide an additional layer of protection. GFCIs are designed to detect small imbalances in the current flowing through a circuit and quickly interrupt the power supply. This can help to prevent electrical shock, even if the circuit is not properly grounded. GFCIs are typically installed in areas where there is a high risk of water exposure, such as bathrooms, kitchens, and outdoor locations. However, GFCIs can also be used in other areas of the home to provide additional protection. When installing GFCIs, it is important to follow the manufacturer's instructions and to test the GFCI regularly to ensure that it is functioning properly. Proper grounding is essential for electrical safety. By understanding the principles of grounding and by following the applicable codes and standards, you can help to ensure that the electrical system in your home is safe and reliable. Remember that working with electricity can be dangerous, and it is always best to consult with a qualified electrician if you are not comfortable performing the work yourself. Electrical codes, such as the National Electrical Code (NEC), provide detailed requirements for grounding electrical systems. The NEC specifies the types of grounding electrodes that are permitted, the size of the grounding electrode conductor, and the methods for installing grounding conductors. It is important to be familiar with the NEC requirements when designing and installing electrical systems. Regular inspection and testing of the grounding system is also important. Over time, connections can corrode and ground rods can deteriorate. Regular inspection and testing can help to identify potential problems and ensure that the grounding system is functioning properly. Testing of the grounding system typically involves measuring the resistance of the grounding electrode system. A low resistance indicates that the grounding system is effective at providing a low impedance path for fault currents. If the resistance is too high, it may be necessary to install additional ground rods or to replace corroded connections. Grounding is not just about safety. It also plays an important role in the proper functioning of electrical equipment. A properly grounded electrical system can help to reduce electrical noise and interference, which can improve the performance of sensitive electronic devices. Grounding can also help to prevent damage to electrical equipment caused by voltage surges. Voltage surges can occur due to lightning strikes, power outages, or other events. A properly grounded electrical system can help to dissipate the energy from voltage surges, protecting electrical equipment from damage. In summary, grounding is an essential aspect of electrical safety and system performance. Understanding the principles of grounding and following the applicable codes and standards is crucial for ensuring a safe and reliable electrical installation. Always consult with a qualified electrician if you have any questions or concerns about grounding your electrical system. Grounding ensures a low impedance path for fault currents, enabling overcurrent protection devices to quickly trip and energize the circuit. This reduces the risk of electrical shock and fire. Grounding also stabilizes voltage, minimizes electrical noise, and protects sensitive electronic equipment from damage. A properly installed and maintained grounding system is a cornerstone of electrical safety. Grounding to metallic water pipes was once a common practice, but it is now generally prohibited by electrical codes. This is because water pipes can be made of non-conductive materials such as PVC, or they may be disconnected during repairs or renovations. This can interrupt the grounding path and create a dangerous situation. Similarly, grounding to gas pipes is strictly prohibited due to the risk of fire or explosion. Gas pipes carry flammable materials, and any electrical fault could ignite the gas. The NEC in section 250.52 A1 specifies that a metal underground water pipe shall be supplemented by an additional electrode. The supplemental electrode shall be a ground ring, concrete encased electrode, or ground rod. This ensures that there are two independent grounding paths, providing redundancy in case one path fails. Ground rods are a common and effective means of providing a grounding electrode. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to a depth of at least 8 feet. The NEC in section 250.52 A5 specifies the requirements for ground rods. The rods must be at least 8 feet long and 5/8 inch in diameter. They must also be installed so that at least 8 feet of the rod is in contact with the soil. When multiple ground rods are used, they must be spaced at least 6 feet apart. Concrete encased electrodes, often referred to as UFA grounds, are another effective means of providing a grounding electrode. A concrete encased electrode consists of at least 20 feet of bare copper conductor encased in concrete that is in direct contact with the earth. The NEC in section 250.52 A3 specifies the requirements for concrete encased electrodes. The concrete must be at least 2 inches thick and must be in direct contact with the earth. The copper conductor must be at least 4 American wire gauge and must be installed within the concrete. Ground rings are another option for providing a grounding electrode. A ground ring consists of a bare copper conductor that is buried in the earth in a continuous loop. The NEC in section 250.52 A4 specifies the requirements for ground rings. The conductor must be at least 2 American wire gauge and must be buried at a depth of at least 2.5 feet. The ground ring must encircle the building or structure. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC, in Table 250.66, provides a table for determining the size of the grounding electrode conductor. For example, if the service entrance conductors are 2/0 American wire gauge copper, the grounding electrode conductor must be at least 6 American wire gauge copper. The equipment grounding conductor provides a low impedance path for fault currents to flow back to the electrical panel. The NEC in section 250.118 specifies the types of conductors that are permitted for use as equipment grounding conductors. These include copper or aluminum wire, rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and flexible metal conduit. Ground fault circuit interrupters, GFCIs, are devices that are designed to protect people from electrical shock. GFCIs detect small imbalances in the current flowing through a circuit and quickly interrupt the power supply. The NEC in section 210.8 specifies the locations where GFCIs are required. These include bathrooms, kitchens, garages, outdoor locations, and other areas where there is a high risk of water exposure. Arc fault circuit interrupters of size are devices that are designed to protect against fires caused by arcing faults. Size detect arcing faults, which are dangerous electrical conditions that can cause fires. The NEC in section 210.12 specifies the locations where F-size are required. These include bedrooms, living rooms, dining rooms, and other areas where people are likely to be sleeping or spending time. Surge protective devices, SPDs, are devices that are designed to protect electrical equipment from damage caused by voltage surges. SPD divert surge current away from sensitive electronic equipment, protecting it from damage. The NEC in section 230.67 specifies the requirements for SPD. SPD must be installed at the service entrance and at other locations where sensitive electronic equipment is located. Regular inspection and testing of the grounding system is essential for ensuring its continued effectiveness. Over time, connections can corrode and ground rods can deteriorate. Regular inspection and testing can help to identify potential problems and ensure that the grounding system is functioning properly. Testing of the grounding system typically involves measuring the resistance of the grounding electrode system. A low resistance indicates that the grounding system is effective at providing a low impedance path for fault currents. If the resistance is too high, it may be necessary to install additional ground rods or to replace corroded connections. When working with electricity, it is important to follow all safety precautions. Always turn off the power to the circuit before working on it. Use insulated tools and wear appropriate personal protective equipment such as gloves and safety glasses. If you are not comfortable working with electricity, it is best to consult with a qualified electrician. A licensed electrician has the knowledge and experience to safely and effectively install and maintain electrical systems. Hiring a licensed electrician can help to ensure that the electrical system in your home is safe and reliable. Grounding is a critical aspect of electrical safety. By understanding the principles of grounding and following the applicable codes and standards, you can help to protect yourself, your family, and your property from electrical hazards. It is always best to err on the side of caution when it comes to electrical safety. If you have any questions or concerns, consult with a qualified electrician. They can provide expert advice and assistance to ensure that your electrical system is safe and compliant. Grounding is not a one-size-fits-all solution. The best approach to grounding depends on the specific characteristics of the electrical system and the building. A qualified electrician can assess the situation and recommend the most appropriate grounding methods. They can also ensure that the grounding system is properly installed and tested. Remember, electrical safety is not a luxury, it is a necessity. Take the time to ensure that your electrical system is properly grounded and protected. It could save your life. And be sure to regularly inspect the components as time goes on to ensure the wiring and grounding is still as sound as the day it was implemented.